Hello everyone. In this video we are going to talk about the method of taking derivatives called logarithmic differentiation. So as you might have guessed from the name, we're going to need to know some things about log in order to use it to take derivatives here. So let's remind ourselves of some properties. So first let's talk about the derivatives. So here I'm always going to mean the natural log. And so the derivative of the natural log, right, is 1 over x. So what happens if we take the derivative of natural log of some inside function instead of just x? So here we'd be using the chain rule, right, where f of x is my inside function. And so when I take the derivative of my outside, I'm going to get 1 over, I plug in my inside, f of x, times derivative of the inside. My inside is f of x, so this is just f prime. So in general, I'll get f prime of x over f of x. This is just kind of a nice thing to know. You always have a pretty nice form if you're taking the derivative of the natural log of something. And finally, what's going to be most useful for us, since we just talked about implicit differentiation, is that if y is some implicit function of x, then the derivative of the natural log of y is going to be 1 over y times dy dx. Or you might see it as, y prime over y. All right, so those are some derivative properties. And then let's remind ourselves of how log works with multiplication, division, and exponents, right? So we have the property that the natural log of a product is going to be the sum of those two things, kind of breaking up that product, right? So it's the natural log of f plus the natural log of g. If you have a quotient inside, well, a quotient is basically multiplication by 1 over, or to the negative 1 power, and that's going to kind of correspond to subtraction here. So I have natural log of f of x minus the natural log of the denominator, g of x. And finally, if we have some function to another function power, then the power comes down out front, and so this ends up being g of x times the natural log of f of x. All right, so all of these things are going to be very useful, and it turns out they're going to allow us to take kind of shortcuts in taking derivatives of some functions. So how is this going to be useful for us, and what does it have to do with derivatives? Well, I'm interested here in finding dy dx. So if you look at it, that process should seem pretty intimidating, right? Looks like I do a quotient rule, but within the quotient rule, my top has, 3 product rules. My bottom has product rule and also a chain rule with the square root of x plus 3. It's going to be a lot of work, and it's going to be pretty messy. So what we're going to do is use the natural log to simplify things. So we're going to just take the natural log of both sides here. So we've got the natural log of y is the natural log of this big thing. So why is this useful? Well, we can use those properties, right? And so if we use those properties, we can split multiplication into addition. We can split division into subtraction. We can get rid of this root because that's really just a power. And so suddenly we can rewrite this like this by splitting the division, and then I'm going to split the multiplication inside each one. And so we'll get, and then finally I can simplify a few things, right? So the natural log of e to the x, well, that's just x, right? And the natural log of x squared, I can bring this power down, and square root of x plus 3 is x plus 3 to the 1/2, so I can bring that power down as well. Okay, so now I've got this long string of stuff. Now I can take a derivative, right? My goal is to find dy dx, so I'm going to go ahead and try to do that. So if I take the derivative on the left, so we talked about before, this is implicit because we've got our y here. So we get 1 over y dy dx. Derivative of a constant is 0. Derivative of the natural log is 1 over x plus 1. Right? We said the natural log of this inside function, we should get the derivative of the inside function, negative sine x, over our original cosine x, because it's like 1 over cosine times derivative of cosine. That's 0, minus 2 over x, and then finally minus 1/2 times 1 over x plus 3 times the derivative of x plus 3, which is 1. And so just 1 over x plus 3 from the chain rule there. And so if I want to solve for dy dx, I'll just multiply over by y and gather some like terms here. So it's really like negative 1 over x plus 1. That's tangent, sine over cosine, and minus 1 over 2x plus 6, multiplying through that too. And then our last thing here, so, with implicit differentiation, we're usually fine having a y, but this really isn't implicit, right? Because our function to start with was written explicitly in terms of x. So we should be able to do that again, and we'll just substitute in our y, okay? And so this would be our final answer. And so this process is called logarithmic differentiation. And so for your first exercise, I want you to use logarithmic differentiation. So again, take the natural log of both sides, so it allows you to simplify this right side to find dy dx for this nasty looking thing. So a natural question you might have is, do we actually need this? I mean, it seems nice, right? Like we make the process much smoother for these nasty things, but we could have gotten away with just like chain, product, quotient, right? It just would have been more work. So do we really need logarithmic differentiation? And the answer is actually yes. So let's think about the function y equals x to the x. So think about our tools thus far. Is this power rule? Well, no, right? Because power rule says it should be x to some constant power, where here this is a changing power. And similarly, right, it's not exponential, because that would be like some base to the x, where the base is a constant. But again, we have a changing base and changing exponent here. And it's not a product of things, it's not a quotient of things, there's no inside, well, I mean, like the inside is x, but we, again, can't really deal with this like changing base. So none of our tools actually apply to this thus far. However, we know that the natural log makes powers much easier. So let's go ahead and take the natural log of both sides. Right? So this is natural log of x to the x, but what does that equal to? Well, that power just comes down, and so we get x times the natural log of x. Well, once we have this is just a product rule, right? So on the left side, if I take the derivative, I get 1 over y dy dx, and on the right side, I will get x times 1 over x plus 1 times the natural log of x. And so dy dx is then y times, well, x and 1 over x cancel to 1, plus the natural log. And so my final answer, if I substitute in for y again, right, because I know y is x to the x, I get x to the x times 1 plus the natural log of x. And so this is something we could not have done before, and using those log properties, we can actually do pretty quickly using logarithmic differentiation. So let's do one more example to kind of, again, look at this process. So here we're going to take the derivative of the natural log of x to the tangent x. And so in general, like, when do you want to use logarithmic differentiation? It is for things like this. So it's going to be, some function base and some function in the exponent where both of these are changing. So, if one of them is constant, it's pretty easy. You don't need this method. But if both of them are variable, then you're going to want to use logarithmic differentiation. Okay? So you're looking for things that look like this. So again, we can just say y is this function. And we always just want to take the natural log so that we can bring down this power, right? So the natural log of y is, I'm just going to go ahead and bring it down. So it's tangent x, bring down that power, times the natural log of that inside, the natural log of x. And again, it's going to be product rule, right? So once you start taking the derivative, which you can do at this step, we have 1 over y dy dx is, so our derivative of tangent is secant squared. And then we have the natural log of the natural log plus tangent times, so what's my derivative here? So ln of x is my inside and it's my outside. So I want to start with 1 over, plug in my inside, natural log of x, times derivative of the inside, 1 over x. Okay? And so your final answer, I'm going to multiply over by y. Y is ln of x to the tangent x. And then times this whole thing. So secant squared x, natural log of the natural log, plus tangent x over x ln x. And that would be your final answer. And so to close with the second exercise, I want you to find the derivative with respect to x for y, which is sine x to the cosine x power. Thank you for watching.